In this video, we will discuss the first law of thermodynamics, which tells us how energy is conserved in a system. Let us begin by the concept of internal energy. Consider a bottle of water sitting on a table. We will treat the water as our system, or the thing that we are studying. What are some common types of energy that we can associate with this bottle of water? First, notice that the bottle is elevated from the ground. Because of its position relative to the ground, the system has gravitational potential energy. In general, the higher the object is, the greater its potential energy becomes. Additionally, if we were to move this bottle, the system would have kinetic energy, which is the energy associated with motion. And the faster the object moves, that is, the greater its velocity, the greater its kinetic energy becomes. So far, the energies we have discussed are macroscopic forms of energy. These are energies associated with the motion and position of the system as a whole. Now, aside from these macroscopic energies, we also have internal energy. From the word internal, we can already guess that it has something to do with what is happening inside the system. By definition, internal energy is the energy of the particles that make up a substance. In this case, internal energy is related to the water molecules. From a macroscopic point of view, the water looks completely still. However, if we look more closely, if we zoom in to the microscopic level, we see that the molecules of water are not at rest. These molecules are constantly moving in random directions. Their motion includes translational, rotational, and vibrational motion. Because of this continuous molecular motion, the water possesses molecular kinetic energy. But that's not all. The water also has molecular potential energy. Water molecules interact with one another through intermolecular forces, and within each individual water molecule, the atoms are held together by chemical bonds, which also store potential energy. Now, when we take the sum of these molecular kinetic and potential energies, we get what we call the internal energy of the system. As you can see, the internal energy of a substance is made up of countless microscopic energy contributions, from molecular motion to intermolecular and intramolecular interactions. Because of this complexity, measuring the absolute value of internal energy at each point in time is extremely difficult. However, this is not a disadvantage, because thermodynamics is more concerned on changes in internal energy rather than its absolute value at a certain point. Now, how does the internal energy change? Let's go back to our example, the water. Suppose we heat the water on a stove. After some time, we notice that something is happening in the water. It starts to move more vigorously, and small bubbles form and rise to the cover. At the microscopic level, the water molecules are becoming more energetic. They move more rapidly in random directions. Now, faster molecular motion or higher velocity means greater molecular kinetic energy. And since this kinetic energy contributes to internal energy, the internal energy of the water increases as well. Additionally, using a thermometer, we can observe this change. As heat is added to the system, the temperature rises, and this measurable increase in temperature reflects an increase in the system's internal energy. So while we may not be able to measure internal energy directly, we can track changes in it through observable quantities such as temperature. At this point, it is important to clarify that heat is not the same as temperature. Temperature is a measure of the average kinetic energy of the particles within a system. The greater the average kinetic energy of the particles, that is, the more vigorously they move, the higher the temperature of the system. Heat, on the other hand, refers to the transfer of energy to or from a system. It is often called energy in transit because it is not stored in the system. It is not something a body possesses. It only represents the energy transfer. Conversely, internal energy is contained in the system. Now, let's look at another way the internal energy of a system can change. Work. Imagine a gas contained inside a cylinder fitted with a movable piston. When the piston is pushed downward, a force acts through a distance, and work is done on the gas. As the piston moves downward, the gas is compressed and the molecules are forced closer together. Occupying a smaller volume, the molecules collide with one another more frequently and with greater intensity. Since faster molecular motion corresponds to greater molecular kinetic energy, the internal energy of the gas increases. And like heat, work is not something the system stores. Both heat and work refer to the energy being transferred to or from the system. We now have two ways by which energy can be transferred to or from a system: heat and work. The first law of thermodynamics brings these ideas together. It is a statement of conservation of energy. It states that energy can neither be created nor destroyed, only converted from one form of energy to another. This idea is commonly written as delta U equals Q plus W. This equation tells us that the change in internal energy of a system is equal to the energy added as heat plus the energy added as work. By convention, the variable Q becomes negative when heat is removed from the system. Similarly, the variable W representing work becomes negative when the system does the work, such as when the gas molecules pushes the piston away. This transfers the energy from the gas molecules to the piston. Additionally, this form of the first law applies to a closed system where no mass enters or leaves the system. For open systems, the expression looks different because mass can cross the system boundary. When mass enters or leaves a system, it carries energy with it, in addition to any energy transferred as heat or work. Despite these differences in form, the underlying idea remains the same. Energy is conserved, which is the central message of the first law of thermodynamics.